okay, because this is a nice recap. Okay, so like I was mentioning yesterday, we discussed section 8.7, Taylor and Maclaurin series, and we found a Maclaurin series for the function f of x equals cosine of 3x over 4. We discovered by following the Maclaurin series formula and computing derivatives, after we got 4 or 5 terms of the 4 or 5 non-zero terms of the series, we're able to then, usually that's enough information so that we can write down what the series is. And that's what we did. We found the Maclaurin series for the cosine of 3x over 4, and then we found its interval of convergence as well. And then we had a second problem where we wanted to find, and remember, of course, the Maclaurin series is when you're expanding around the value a equals 0. Then we found the Taylor series for a different function. We had the function, this was our second example. Our f of x equals 1 over square root of x was the next function, and we wanted to find a Taylor series for that function centered at a equals 9. And the reason we chose a equals 9 is because then when you compute the derivatives, which are needed to find the terms of the Taylor series, the derivatives can be easily evaluated at a equals 9 because the square root of 9 is 3. Okay, and so we found that Taylor series, and it took a little bit of thinking, but we did get it. All right, so so basically what you did yesterday was you actually constructed a Maclaurin series and a Taylor series from scratch based on the definition of what a Maclaurin series is and a Taylor series is. Today, though, we're gonna continue, but we're gonna actually utilize a table of Maclaurin series, because just like with the remember section 5.8, the tables of integration tables. Those are integrals that mathematicians over the years have, hold on, let me just, yeah, section 5.8 was integration using tables. So there are tables of integrals, right? And similarly with Maclaurin series, there are tables for Maclaurin series. And we're going to make use of that to help us with the examples today from section 8.7. So on that note then, let me share this file here. I'm trying to, for some reason I can't get it up. Okay, hang on. Okay, let's do a few examples here. Okay, so let me give you a moment to copy down this this example, and then we'll talk about it. Okay, so we want to evaluate this definite interval correct to within 5 decimal places. And the function itself is the sum of the arctangent of x cubed plus the sine of x cubed. And of course, we cannot get the antiderivative of this function. So therefore, we will utilize Maclaurin's series. We'll find Maclaurin's series for the arctangent of x cubed and the sine of x cubed. Okay, that's what we have to do first. So, all right. I'd like to now go to the solution. Does everybody have this example copied down all right? Okay. So what I have here is a table. Well, what I have here is actually a formula sheet. It's a formula sheet that has the Taylor series formula. And you know the Maclaurin series is the same as the Taylor series, but A equals 0. The Maclaurin series is just a special case of the Taylor series where A equals 0. All right? And then below are some different Maclaurin series. There's a reference table, and this is also in your textbook in section 8.7. If you go into section 8.7, and let's see here. 8.7 has a lot of good examples. It's table 1 in section 8.7, and it's later in the section. It comes after example 9. All right, what you have here are, let's see, you have 1, 2, 3, 4, 5, 6 very standard functions along with their Maclaurin series for each function. And then intervals of convergence. Okay, so my table is a little different from the table in the book because the table in the book, instead of giving intervals of convergence, it gives a radius of convergence. So that's fine, but I always like having the interval of convergence because if you know the interval of convergence, then you can get the radius of convergence easily. So all right, now in our problem here, fortunately, the function where we have to get the power series involves the sum of an arctangent and a sine. So we're not going to derive this. We're gonna need to find the Maclaurin series for the arctangent of x cubed and the sine of x cubed. But we're not going to derive that from the definition. We're not going to derive it from scratch like we did yesterday because we have these nice formulas that we can use. So the sine of x, I have the power series here for the sine of x, and all I need to do is substitute in for x cubed. Similarly, for the arctangent of x, I have the power series. And so to get the power series for the arctangent of x cubed, all I need to do is substitute in x cubed for x. And that's the idea that we treat x cubed like an apple. Okay, so we talked about, we did an example yesterday where we did that. Okay, all right, so that being said, are there any questions regarding these formulas? All right, well, let's proceed on then. So, okay, here's the power series for the arctangent of x. Now I can use that to get the power series for the arctangent of x cubed by just substituting x cubed in for x. Okay, so I'll give you a little time to copy that down. Okay, and are there any questions up to this step here? The x to the third raised to the 2n plus 1 power, by the way, you're raising x cubed to a power, so you just multiply the exponents. And 3 times 2n plus 1 is 6n plus 3. That's how we get that. All right, and then, of course, for the sine of x cubed, well, the sine of x cubed, we would just substitute in x cubed for x and proceed forward with that, proceed forward to get that power series. Okay, so I want to give you a moment to copy that down and let me know if you have any questions. Okay. All right. Once again, are there any questions so far? Are we good? Josiah asked, will that formula sheet be given to us? Yes. What I would like to do, I mean, right now, of course, you have it in the recording, but of course, what I want to do is when I update the course content for section 8.7, when I put it in the Blackboard, I'll include a link to that that formula sheet. Good question. All right, Josiah, sound good? Okay, great, great. Okay. So, okay, well, let's proceed to the next page then. Now we have our two power series for the arctangent of x cubed and the sine of x cubed. And we're going to substitute those in for the functions. So I will do that. So of course, the original problem was find the integral from 0 to 0.2 of the arctangent of x cubed plus the sine of x cubed. So I'm plugging in, let's see, Maxim, hold on, has a question here. The old formula sheet. Maxim says, what happened to the old formula sheet? I don't know if there was an old formula sheet, was there? I have to, that sheet that's in the recording, I will upload that in Blackboard so you have access to that. However, until then, you have in your ebook, section 8.7, that the table is also in section 8.7 towards the end of the section. If you look in your ebook just before example 10, the table is there as well. Oh, the table of integrals. Let's see. Let's see. Did I think, let's see, Maxim's asking about the table of integrals. Did I email you that table, Maxim, or was it in Blackboard, as you recall? May I see, it was probably under the old syllabus and another information folder, right? Okay, I'll also, table of integrals, it was an announcement, okay. Yeah, I'll make sure you have access to that table. Okay, thank you for reminding me about that. All right, no problem, you're welcome. All right, so the integral of the sum of these functions is the integral then of the sum of the power series. But now we have the sum of two power series, okay, and let's see. The sum of two power series. Notice that the sums both start with the same index, n equals 0. Intuitively, what would you like to do with, it says add the sums of the power series. So you have a power series plus another power series. And both power series start at n equals 0. Intuitively, what would you like to do with those two power series? Intuitively, what might be good to do? What might be a natural thing to do? Well, let me ask you, can we combine the two power series? Could we combine these power series together and write it as one power series? Would we be able to do that? We could, Josiah, absolutely, because they start at the same index, n equals 0. And so we're going to do that. We're going to do that. But I want to be a little careful here. What I'm going to do, hold on here. Let me just check what I'm going to do first is I will get there. But I guess I could do that now. But what I choose to do now is I have the integral of a sum. So that equals the sum of the integrals. That's what I do first. Okay. I didn't look ahead enough in my notes. That's what I do first. So the integral of the sum is the sum of the two integrals. And then the integral of a sum is the sum of the integrals. So I utilize that to get us down to this step here. So let's make sure everybody's comfortable. Are there any questions? All right, well, now we have here in front of the first integral, -1 divided by 2n plus 1. That's a constant with respect to that integral. The integral is with respect to x. So -1 to the nth power divided by 2n plus 1 is a constant. It's not dependent on x. It's dependent on n. So we can pull out that in front of the integral. Similarly, the second integral, the -1 over 2n factorial, that can also be treated like a constant with respect to that integral. So you can pull out those constants. And then you get to this stage. Step by step. You do the work step by step. And it makes it easy. And now, of course, we get the antiderivatives of those two functions, and that brings us to this step here. And at this point now, we've integrated, and so we introduce constants of integration, C1 and C2. Okay, are there any questions up to this step here? Are there any questions at all? Okay. I'll move to the next page then so we can continue. Everybody's good? Okay. Okay. So here's where we're at. All right. I just rewrote what was on the previous page, but now I have a plus C because I combined C1 and C2. And now at this stage, the sum of these two power series I could write as one power series because they both start at the same index. If they did not start at the same index, n equals 0, if the first series started at n equals 0 and the second series started at n equals 1, you couldn't just combine the power series. You would have to make an adjustment on the indices so that they start at the same value. And this is something when you do problems involving differential equations, power series solutions for differential equations, which are very important. You'll be doing that kind of thing. But for now, we just combine. And if you don't mind, I'll rewrite my my sum in like this. I have a x to the 6n plus 4, well, -1 to the n times x to the 6n plus 4 over 6n plus 4. That's a common factor between the two expressions, so I factor that out. How many incidentally find it helpful using the pen to sort of circle things as I discuss things? Is that I would imagine that would be helpful. How many of you find that helpful? Okay, thank you, John. Thank you, Robin. Thank you, Josiah. Great, great. All right. Thank you, Francesca. Thank you. That's great. Okay, so now we're here, and we are ready now to evaluate our integral using our power series. Okay, are there any questions before we move to the next page? Okay, okay. So now the integral from 0 to 0.2 of the arctangent of x cubed plus the sine of x cubed dx is equal to this power series evaluated at 0.2 for the top limit and 0 for the bottom limit. Now, when you put, of course, you're going to put 0.2 in the series first, as I show you here. And then you're going to put 0 in the power series. But when you do that, when you put 0 in the power series, you're going to get 0, right? So 0.2 goes in first to the power series, minus, and then 0 gets put into the power series. But when x is 0, you're adding up a bunch of zeros, and so you get 0. Now this is a special kind of series. There's something special about this series. We want to evaluate it correct to within 5 decimal places. What theorem can we use to help us? What theorem can we use to help us? Notice we have a -1 to the nth power as a term in this series. So what kind of series is this? That's right, Josiah. It's an alternating series. And therefore, we can use the alternating series estimation theorem to help us answer this question. Okay, and so what we do is, how do we do that? Well, all right, we're going to let n equals 0 first. When n equals 0, you'll get this first term here when n equals 0. Okay, because like 0.2 to the 6n plus 4, that's 0.2 to the 6 times 0 plus 4, that's 0.2 to the 4th. Okay, and like 1 over 2n plus 1, that's 1 over 2 times 0 plus 1, that's 1 over 1. All right. And then you're going to have another term, the next term, like so this is when n equals 0. And then you have n equals 1 for the next term. So what I've done is I've written down 2 terms of the series. And the question is, should I write more terms down in the series? Well, I don't want to waste time. I mean, I have to write some terms of the series down, but maybe one or two is all I need. The reason I'm thinking this is because the second term of the series has that 0.2 to the 10th power in it, and that's going to make that term be very small. And remember, since we want correct to within 5 decimal places, we want our power series estimate of the integral to be correct within 5 decimal places. We are looking then to find the first term that is smaller than 5 over 10 to the 6th power. So maybe that term will work. So what I do is I evaluate the terms. The first term is 0.00080. That's greater than 5 over 10 to the 6th. However, the second term is 0.00000000512. That's less than 5 over 10 to the 6th power. Okay, that's less. 5 over 10 to the 6th power, one moment here. On your calculator, that's 5e to the negative 6. So that's 5 times 10 to the negative 6. So that means we have 5 zeros followed by a 5. All right, that's what, if you write this out in decimal form, you have 0.000005. And our second term of the series is smaller. So therefore, to get our approximation correct to within 5 decimal places, we only need to take one term of the series. We only need one term. Okay? And this is how you apply the alternating series estimation theorem. And remember, in your exam, the second part of the exam, you'll have some problems in part 2 where they ask you estimate the integral correct within 4 decimal places, 5 decimal places, whatever, and pretty much those are, I would think those are going to be all alternating series. But what I'm trying to say is, when you evaluate the integral correct within a certain number of decimal places, you can't just give an answer. You have to justify your answer, and you do that, in this case, using the alternating series estimation theorem. And you have to write the terms out, and you have to do this analysis. I need to see that for the exam in order for you to get credit for that portion of the problem, and it's an important part of the problem. Okay? You can't just say, I used the alternating series estimation theorem and my answer was this. That's not showing the work, right? So, all right, just stick it. All right, so let's continue then. Let's continue. Are there any questions about this here before we move on? Okay. All right, so therefore, by the alternating series estimation theorem, okay, the integral, this definite integral, is approximately equal to 0.00080, correct to 5 decimal places. I mean, it's absolutely fascinating. You have this level of accuracy, and you only needed one term of the power series. And it's actually correct to 7 decimal places, because that second term is less than 5 over 10 to the 8th power. So, you have a tremendous accuracy. And, it's no problem computing 0.2 to the 4th over 4 times 2. You could do that by hand easily. You did that kind of thing in elementary school, right? And a computer could do it very quickly, right? So, All right, so this is, just see here. Just trying to see something here. Yeah, it even mentions in the book, it's actually in section 8.6, they mention it in the introduction, that computer scientists will use the power series to represent functions on calculators and computers. So it's just a comment. You know, is anybody a computer science major here? Okay, usually there's one. Is anybody minoring in computer science? Okay. Okay, great, Suha. All right, great, great. And so, you know, good stuff here, Suha. Good stuff for Suha, good stuff for everybody. So you have to imagine back, you know, these concepts are several hundred years old. And back then, you know, mathematicians, even older than that, mathematicians needed to, you know, they needed to compute integrals. How are they going to do it? They can't get the antiderivatives. Well, they can use the power series to help them, because when you compute a power series, when you're using a power series to estimate an integral, all that's being let me just see here one moment. What you're utilizing really is a polynomial, right? The power series is like the Maclaurin series, Taylor series, section 8.7 is really a polynomial. It goes on forever, but polynomials, you can compute values of polynomials just by multiplication, addition, subtraction, and division. So that's all stuff that can be done easily. All right. And of course, the computer can do it very quickly, right? So, all right. Are there any questions on this before we go to the next example? Okay, let's move to the next example then. Okay, now here, well, let me let you copy the example down. Okay, so in this problem, we want to use multiplication of power series to find the first three non-zero terms in the Maclaurin series for this function. So if we were to use the definition of the Maclaurin series, which is the same as the definition of the Taylor series, except a equals 0, we could compute the derivatives of the first three derivatives of this function, and then evaluate the function at 0 and construct it. We could answer the question by doing that, but again, you know, we have in that table that you saw in the recording, and my table, and then and the table in the book, of course, we have Maclaurin series for e to the x. Hence, we can get the Maclaurin series for e to the 2x. And also, we have a Maclaurin series for the log of 1 plus x. And therefore, we can get the Maclaurin series for the log of 1 plus x squared. Okay, so now I want to mention, I'll just mention this. It should go without saying, but these concepts in section 8.7, you know, of course, I don't want you to use them for section 8.6. Okay, section 8.6 was like for those kind of problems, the section 8.6 problems, I want you to use the concepts from section 8.6 to help you get the answers. So I don't want you to use Taylor-Maclaurin series to help you with section 8.6, okay? Because section 8.6 comes before section 8.7. So like your exam 4 part 2 deals with section 8.6. So I'm just mentioning that because sometimes when I see students do problems, they're using concepts that they didn't learn yet. And when you learn section 8.6, you didn't learn section 8.7 yet. So, and so, you know, for section 8.6 problems, please just, you know, use what you learned in section 8.6 to help you answer those questions, because that's what I'm looking for in your work. Okay, all right. So, but now, you know, here we are, section 8.7. We want to find the first three non-zero terms in the Maclaurin series for this function. So what I'm going to do is I'm going to make use of the fact that I have a Maclaurin series for an exponential function and a log function. And once I have the two series, I can multiply the power series. So you see here we have the product of one function times another function. So if I get the power series for the first function and the power series for the second function, I can multiply the two power series together to answer this question. So on that note then, let me go forward here. Here's the table. And again, this table is in your book, section 8.7. Here's the power series for e to the x. Okay. And we'll use that to help us get the power series for e to the 2x. And then here's the power series for the log of 1 plus x. And we'll use that to help us get the power series for the, what was it? The log of 1 plus x squared. All right, and I'll move to the next page, but are there any questions so far? Okay. Okay. Well, let's proceed on. So what I did was, for e to the 2x, I substituted 2x in the power series for e to the x and got this power series. But I'm writing the power series out in terms of the terms of the power series. I mean, I could write a sum, right? I could write a sum here of of, hold on here, 2x to the n over n factorial. But equivalently, I'm writing the power series where I enumerate some terms. And I do that because there's a reason I do that, okay? Now, the power series for the log of 1 plus x squared, okay, again, power series for the log of 1 plus x squared, if I put in x squared for x, you're going to get the sum where, and you know, the n equals 1 to infinity. I'm not writing the n's in just because I want to save a little time here. But -1 to the n minus 1 x to the n power over n. Okay. But again, I'm choosing, instead of writing the series in the formula form, I'm writing the series this way, where I enumerate some terms. Okay. Maybe I'll put in the indexes here. It doesn't hurt, right? Put the indexes in. I mean, it is important actually because the first series starts at n equals 0. The second series starts at n equals 1. So are there any questions so far? I think I have an error here. Hold on. This should be x squared, right, to the nth power on that second power series. So, okay, any questions here? All right, so when you multiply a sum by another sum, really in order to do it, at least for now, what you have to do is you have to write out terms of the first sum and terms of the second sum, and then multiply them out, basically using the distributive property. And then, you know, you'll detect a pattern, and then you can get the series for the product of the two functions. However, in this case, all they're asking you to do is find the first three non-zero terms. So the first three non-zero terms in the Maclaurin series would be the terms with the lowest degree. So, like for instance, you'll notice here I have, you know, I'm writing some terms out. Let me just see here, one moment. Let me make this a little smaller here. So what I'm doing is I'm simplifying the terms in the first series and the terms in the second series before I do the multiplication. I mean, that would make sense. And I know that I'm not going to be using all these terms because I only need the first three non-zero terms in the product. Okay, so only need the first three non-zero terms. Are there any questions so far up to this step? Okay. All right, so, all right. So what is the, let me see. Josiah says, on that step, should there be a 2, let's see, a 2 times x squared over 2 in the first parentheses? Let me see here. Oh, like here. No, good question. So you're referring, Josiah, to this term here, 2x quantity squared over 2. Good. So you'd have 2x, so this term here, 2x quantity squared is 2x times 2x, and then over 2 factorial, 2x times 2x over 2 factorial, that's over 2. So see, you're going to get 4x squared over 2, and that gets you 2x squared. So Josiah wanted to know why we have 2x squared for the third term in that first series as opposed to something else. Okay, great, Josiah, great. Okay, so what is the, when we multiply these two series together, this series by this series, what's the lowest, what's the degree of like the, I mean we know we're going to get a series, but what's the degree of the like first term? What would the degree of the first term be? So all right, let me explain it another way. Here, I have a, so what we're going to do is, like, let's think about the distributive property. If you had A plus B, okay, times C, that would equal AC plus BC, right? Distributive property. So let me be clear here. So what I'm going to do is actually, hold on. Let me even make this more clear. Let me make this more clear. Hold on. You had A plus B plus C plus dot, dot, dot. So that's that, those terms keep going. And you multiply that times D. Then by the distributive property, you're going to get AD plus BD plus CD dot, dot, dot. It keeps going, right? Keeps going. So what we're going to do is we're going to treat the 1 like A. We're going to treat the 2x like B. We're going to treat the 2x squared like C. And then we're going to treat this whole second power series like D. Okay, and this is how we're going to multiply the first power series by the second power series. We're going to take the term, each term of the first power series here, and multiply that term by the entire second power series. If we do that, like when we take a times the d, we're going to get 1 times x squared plus 1 times x to the 4th over 2 plus a bunch of other terms. But I'm only choosing to multiply, do a few multiplications, because I only need the first 3 non-zero terms. So I don't want to multiply more than I have to. So far, are we okay? Are there any questions with how I got that first step there? Okay. Well, now what I'm going to do is I'm going to take the b term, the 2x, and multiply it by the power series, the second power series. So if I do that, I got plus 2x times x squared plus a bunch of other terms. And then finally, I'll take the third term of the first power series, the 2x squared here, and multiply that by power series d. So 2x squared times x squared. Are there any questions up to here? Okay, okay. All right, let me ask you this. You notice I don't do any more. I don't do any more. I mean, we know there's plus dot dot dot. I could take then the fourth term 8x, the fourth term of the first power series. I could take 6x cubed and multiply it by the power series. I could continue, but I don't do any more. Okay, because what's the smallest degree of this power series going to be? What's the smallest degree going to be? What the first term of the power series? What's its degree? That's what I'm asking. I'm not saying it right. After we take the product of these two power series, what's the degree of the first term going to be? That's right, Robin. It's going to be 2. Absolutely. Okay. What's the degree going to be of the second term of the power series? 3. That's right, Robin. We can see that because we have a 2x times x squared. That's going to get us 2x cubed. That's right, Ryan. Absolutely. So I have an x squared term, an x cubed term. What would the next term be? What would the degree be on the next term? That's right. That's right, Ryan and John. 4. Because look here, you have 1 over negative x 4 and 1 times negative x to the 4th over 2. Okay, so the reason I don't multiply, well, why don't I take the 8, 6 here? Why don't I take the 8, 6? Why don't I bother to take the 8, 6x cubed and multiply it by d? Why don't I bother to do that? For some reason, I'm not going to bother to take 8, 6x cubed and multiply it by the series d, that second series. There's a reason for that. Let me ask you, if we did take 8, 6x cubed and multiply it by that second series, what would the degree be of like the smallest of the first term? 8, 6x cubed times x squared. What's the degree of that of that term? 5. All right, John, good. What's the degree of the next term? 86x cubed times negative x to the 4th over 2. What's the degree of that term? That's right, Robin, 7. So very good. So what's happening is, see, I only want the first 3 non-zero terms, and that's going to be just the x squared, an x squared term, an x cubed term, and an x to the 4th term. I don't need to put any more in. And in WebAssign, they'll ask you to a similar kind of question. But I do note that, the 2x cubed, we know how we got that. That's from 2x times x squared. And the 1 times x squared gets us the x squared term. And then the negative over x to the 4th over 2 plus 2 times x to the 4th gets you 3/2 x to the 4th. Okay? All right, so it's a good problem because it forces you to work. You're basically working with power series. You have to enumerate terms of power series in order to get the answer. So it's a nice problem. Are there any questions on that problem? Oh, Robin says y 3/2. Okay, so this term here is negative 1/2 x to the 4th, right? Negative 1/2 x to the 4th. But then we got another x to the 4th term. Very good question, Robin. We got 2x squared times x squared. That's going to be plus 2 times x to the 4th. So what's negative 1/2 plus 2 equal? 3/2. Okay, excellent, excellent. Are there any other good questions? Okay, I'll stop the recording here.